Let's talk more about the speed of a wave. So as I mentioned in the last video, or one of the previous videos, we can say that the speed of a wave is equal to wavelength times frequency, or we can also write it as the angular frequency over the spring constant. No, that's not the spring constant. That is the wave number. Sorry. I guess that's good I mentioned that so we remember that's the case. So K in this case is the wave number. This equation, again, is a bit deceptive in that wavelength and frequency, and thus angular frequency and the wave number, do not affect the speed of the wave. So we can calculate the speed of a wave knowing both wavelength and frequency, but if we change wavelength or frequency, we are not in turn changing the speed of the wave. So wave speed always depends on the medium the wave is traveling through. And it depends upon what type of wave we're talking about. So as far as our mechanical waves are concerned, right now we're talking about waves on a string. We're talking about sound waves. So these are both mechanical waves in that they require an elastic medium for the wave, that disturbance, to travel through. We are also going to talk about electromagnetic waves and just the fundamentals of the speed right now. All right, so the wave on a string. If you've ever seen a guitar or a violin or a cello, all these different stringed instruments, the speed of the wave on the string is determined by two things. It's determined by the force of tension in the string, so how tight the string is. Every single stringed instrument, in order to tune it, meaning have the string play the pitch that you expect it to, you tighten the pegs and until it's playing the note that you are wanting it to play, that it should be playing. On any given instrument, this tension is really close to the same thing on all the strings. Otherwise, if it wasn't, it would cause the neck. So if I had a guitar, for example, I'll see if I can kind of draw a stringed instrument. So if I have this guitar and I have these strings with their pegs, if the strings were not equally or very closely equally in the same tension, the neck of the guitar would end up experiencing a torque and it would bend, which of course would not be good for the guitar. So we do find that the force of tension is very, very close to the same value in every string. But if we look at the strings individually, they are not the same thickness. So these strings have different thicknesses. In this equation, this mu is called the linear mass density. It is the ratio of mass per length on the string. A thicker string corresponds to a larger mu value. So the thicker strings, the speed is smaller because mu is bigger. That speed being smaller corresponds to a smaller frequency or a lower frequency, and so the thicker strings actually play lower notes, lower pitched notes, which we'll talk about that more in the next chapter. But ultimately, the speed of the wave on a string depends upon the tension in the string and it depends upon the linear mass density of the string. Our author does not write the force of tension as F sub t, writes this as capital T. So tension in the string, if you remember from previous semesters, we used capital T to represent tension. I'm a little hesitant to write capital T because we've been using that for period. But either way, T sub S or F sub T means the tension force in the string. As far as SI units are concerned, that would be measured in newtons. Mu, our linear mass density, SI units, that would be measured in kilograms per meter. And so when we plug in the tension, that linear mass density, we end up with a value for the speed in meters per second, which is appropriate. That's our SI units for speed. All right, now sound also depends upon the medium. The fundamental equation for the speed of sound, though our author doesn't introduce this equation, so you won't be making a calculation with this, but I still want to introduce it. It depends upon the bulk modulus. That's a material property related to the compression of a material. And then this is just regular mass density that we've used before. It's mass per, let's write that a little bit better, mass per volume. And so sound can travel, of course, through air. It can travel through different gases. It can travel through liquids. It can travel through solids. And how fast it travels depends upon what that material is. So steel would have a certain bulk modulus, a certain density, and thus sound could travel at a specific speed through steel. Our author includes a table in the chapter that gives the speed of some of the speed of sound in different materials. If you need to know the speed of, sound in, say, steel, look for that table in the chapter to find the value. As far as the equation that we are going to talk about and use is for the speed of sound in air. Now this is an approximated equation. It looks like this. This is in our test notes. The speed of sound in air does depend upon the density of the air, the humidity of the air, the temperature of the air. We are going to look at that specifically in terms of temperature. So this T with the degrees Celsius here is the temperature of our air in degrees Celsius. So this equation assumes dry air, so very low humidity. It also assumes we're at sea level, so air pressure is 1 atm. You will see also in the test notes, it says V is 343 meters per second for dry air, sea level, and at 20 degrees Celsius. So as we are solving problems that involve sound waves, if there is no temperature given or asked for, and we need the speed of sound, we're going to use the value 343 meters per second. If we are given a temperature, then we're going to use this equation to find the speed at that temperature. We are going to assume this dry air and sea level, And since that's what our author is assuming at this point. So speed of sound depends upon the temperature of the air. Now, electromagnetic waves, again, light is a subset of electromagnetic waves, so visible light. We also have our radio waves, which is going to be any type of signal that's from a broadcast tower, like a TV station, a radio station. Our cell phone signals fall in this category. Microwaves fall in this category. Our microwave ovens, gamma rays, X-rays, ultraviolet, so UV, infrared, IR, is how we abbreviate that. All of these are subsets. They're all individual types of electromagnetic waves. Electromagnetic waves all travel at the speed of light in a vacuum. Meaning the absence of a medium. You might be familiar, we use lowercase c to represent the speed of light. It's approximately 3 times 10 to the 8th meters per second. Every single type of electromagnetic wave travels at this same speed in a vacuum. But similar to other waves, if we change the medium, meaning if the light now is entering our atmosphere, if light enters water, if light enters glass, the speed changes because it is now traveling through a different medium. The equation that represents the speed of light in this new medium is c, the speed of light in a vacuum, divided by what we call the index of refraction. The index of refraction is related to the material itself. Our author gives us a table in the chapter. For example, air, N is 1.0003. Now, when we take this speed of light and divide by 1.0003, we essentially still have the speed of light. So any problem that we look at with electromagnetic waves, we will still usually use this same value in air, just because that index of refraction is so close to 1. But water, for example, has an index of refraction of 1.33. And so the speed of light in water, V in water, we would take that 3 times 10 to the 8th meters per second and divide by 1.33. So the light will travel slower in water. So we get 2.3 times 10 to the 8th meters per second. It slows down, which is also explains why, like if you're in a swimming pool and you look down at your legs, they look different, they look shorter, they look different in general. And that's because as the speed of light changes, the direction the light is traveling in also changes. We call that refraction. And so what we see and observe from the light that comes back out to our eyes looks different than it would in air. And we actually go full circle this semester, and after this section, we'll be talking about electricity and magnetism, and we'll get back to electromagnetic waves. And we'll talk about this concept more, the refraction, the bending, and how the direction changes. Now, one other thing to keep in mind is this speed is changing. Keep in mind, n is always greater than or equal to 1, at least as far as we all know at this point in time. It has not yet been discovered that anything can travel faster than the speed of light. So we expect n to always be either equal to 1, which is for a vacuum. So the absence of a material is defined as n equals 1. For everything else, n will be greater than 1. And that's going to be unique to the material itself. As light enters a new material, so say it was in air and travels into water, the frequency stays the same. The energy of this electromagnetic wave causes molecules within the water, if that's the material it's entering, it causes the molecules to vibrate and oscillate. And they will oscillate at that same frequency. But if the frequency is staying the same and the speed itself is decreasing, if we come back to our equation at the top where we relate speed to wavelength and frequency, the speed changes as the electromagnetic wave goes to a new material. The frequency does not. So if here the frequency has gone down as the light enters water, but frequency is the same, then the wavelength has to go down as well to maintain that equality. We find that the wavelength of whatever electromagnetic wave we're talking about will also decrease by the same amount as the speed of the wave as it enters a new medium. So regardless of the type of wave we're talking about, how fast the wave is traveling is completely and totally dependent on what the wave is traveling through, and also what type of wave it is. So a wave on a string depends upon the tension in the string, the linear mass density of the string, which effectively we can think of as thickness. Sound, we're going to depend on the temperature. Technically, it does depend on the air pressure, the density, humidity, but again, we're just going to simplify that down to being temperature for our intents and purposes right now. And then electromagnetic waves travel at the speed of light unless they're in another medium, and we account for that using this index of refraction. So we'll do a couple examples so that you can see how to use equations, and then we'll talk about the other concepts in this chapter.